Stealth jets explained. Why you can't see them on radar. In the world of modern air combat, stealth isn't just an advantage, it's a revolution. From flying under radar to striking without warning, stealth jets like the F-22 Raptor, F-35 Lightning II, and B-2 Spirit have changed the very rules of aerial warfare. But what exactly makes these planes invisible to radar? And how do engineers design an aircraft that can hide from the most advanced detection systems in the world? Today, we break down the science and secrets behind stealth jets, and why you can't see them on radar. Number 1. What is radar? To understand stealth, we first need to understand radar. Radar, short for radio detection and ranging, works by emitting radio waves and detecting their reflections from objects in the sky. When a radar pulse hits a jet, the energy bounces back, alerting operators to its position, altitude, and speed. The bigger and more reflective an object is, the easier it is to detect. This reflectivity is measured as radar cross-section, or RCS, expressed in square meters. A commercial airliner might have an RCS of 100 square meters. A fighter jet from the 1970s? Maybe 5 to 10. But a stealth jet? As low as 0.0001 square meters, about the size of a marble. Radar works by sending out radio waves. When these waves hit an object like a plane, they bounce back to the radar antenna. The time it takes for the signal to return tells operators where the object is and how fast it's moving. Simple in theory, but deadly in war. Number 2. The shape of invisibility. One of the biggest contributors to stealth is shape. Traditional aircraft have vertical stabilizers, sharp edges, and round noses, all of which reflect radar waves directly back to the radar source. Stealth jets, on the other hand, use planform alignment, where all surfaces are angled to reflect radar energy away from the radar receiver, not back to it. One of the biggest ways stealth jets stay hidden is through shape. Radar waves bounce off flat surfaces and sharp angles. So stealth jets are carefully sculpted to reflect radar away from the source, not back toward it. That's why they often look weird. Take the F-117 Nighthawk, the world's first operational stealth aircraft. Its faceted design, all flat panels and sharp angles, was developed not for aerodynamics but to scatter radar waves like a broken mirror. Later stealth designs, like the F-22 and F-35, use smooth curves and continuous surfaces to achieve the same effect, but with better aerodynamic performance. Even the cockpit canopy is coated with a special material to reduce radar reflections from the pilot's helmet and instruments. Number 3. Radar-absorbing materials. RAM. Shape alone isn't enough. That's where radar-absorbing materials, or RAM, come in. These materials don't just scatter radar, they absorb it, converting the electromagnetic energy into heat, which dissipates harmlessly. These special paints and composites soak up incoming radar waves, converting them into heat, which is far less detectable. RAM can be paint, coating, or composite layers embedded in the jet skin. The F-35, for instance, uses advanced RAM that's baked into its structure, reducing maintenance needs and improving durability. But RAM isn't just applied randomly. Engineers carefully design multi-layer composites with microscopic structures that resonate at radar frequencies, capturing incoming waves like a sponge soaking up water. Number 4. Internal weapon bays. Another dead giveaway on radar? External weapons and fuel tanks. Conventional jets carry bombs, missiles, and drop tanks under their wings, which dramatically increase radar signature. These special paints and composites soak up incoming radar waves, converting them into heat, which is far less detectable. Stealth jets solve this by using internal weapon bays. The F-22 and F-35, for example, carry missiles like the AIM-120 AMRAAM and JDAM bombs entirely within their fuselage. These bays open briefly to launch weapons, then close again, minimizing radar exposure. It's a simple concept with complex engineering behind it, ensuring that the doors open only when absolutely necessary. Number 5. Engine masking and IR suppression. Stealth isn't just about radar, it's also about infrared and acoustic signatures. Jet engines are massive heat sources, and modern infrared sensors can detect them from dozens of miles away. To counter this, stealth jets use flattened engine nozzles, cooling ducts, and exhaust mixers to reduce their heat output. The F-22's nozzles, for instance, are designed not only for thrust vectoring but also for reducing the jet's heat signature. In some cases, the jet's upper surfaces are coated with IR-absorbing materials, further minimizing detection from above by satellites or high-flying drones. Even engine placement matters, buried deep inside the fuselage and covered with S-shaped intakes that hide the spinning turbine blades from radar. Number 6. Electronic warfare and low probability of intercept. LPI radars, like those on the F-35, use frequency hopping, spread spectrum, and low power bursts to avoid detection by enemy radar receivers. It's like whispering in a noisy room instead of shouting. You still communicate, but no one else can hear you clearly. Some stealth jets also jam enemy radars or use decoys like the MALDJ, which mimic a larger radar signature and draw missiles away from the real jet. Number 7. Limitations of stealth. Stealth aircraft are optimized for certain radar bands, typically X-band, used by fire control radars. But lower frequency radars like VHF and UHF can still detect them, albeit with less accuracy. Also, stealth is angle dependent. A jet is most stealthy from the front, but less so from the sides or rear. That's why stealth pilots rely on tactics like flying low, using terrain, and limiting their radar exposure during missions. Maintenance is another challenge. RAM coatings degrade over time and need regular upkeep. In high humidity or sandy environments, stealth coatings can suffer damage, compromising the aircraft's signature. Number 8. The future of stealth. Sixth-generation programs like the US NGAD and Europe's FCAS aim to push stealth even further with adaptive skins, active camouflage, AI-driven signature management, and drone wingmen. China and Russia are also developing their own stealth capabilities, with aircraft like the J-20 and Su-57, though Western analysts debate how stealthy they truly are. Meanwhile, ground-based radars and space-based sensors are catching up. Future air combat might not be about being totally invisible, but about being just stealthy enough while using AI, networked warfare, and speed to dominate the fight. Conclusion: stealth jets are the pinnacle of modern aerospace engineering. They don't rely on brute force or speed alone, but on science, geometry, and electromagnetism to become ghosts in the sky. Radar isn't the only way to detect a jet. Missiles and sensors can also track heat, especially from afterburners and engine exhaust. You can't fight what you can't see, and that's exactly why stealth will continue to be the sharpest edge in air combat. Thanks for watching. If you enjoyed this breakdown of stealth technology, don't forget to like, subscribe, and let us know which jet you want us to cover next.